Florida.
Five.
Okay, 5, 4, 3, 2, 1. Today we're going to look at slightly different shapes than we looked at yesterday. And a very similar concept. We're going to give you a day to work on this. We're going to take, say, a function that we will call g, and another function that we call f. And we will bound that region by a and b. Okay. And what we're going to do is we're going to take the area bounded between the two functions and take like this space right here. And that's the space that we are going to revolve around the x-axis. You see that? So this is empty area. This is area that's filled in. Do you see that when you rotate it, you're going to get a hole or an empty space in the middle? So I'll try to draw a little bit about what that looks like. Let's say that we have... oh, don't like it when I do that. Let's say that we've got let's say that that's our lower space, and when we rotate it around, we're going to get kind of that disk region from yesterday. The difference is that there's going to be a space on the inside that's empty. You don't have to draw it perfect, but you want to be able to visualize what's going on. I'll do the another one right here. What shape does that make?
Oh, like a chalice.
Okay, so the chalice would be kind of like the entire shape, except it have a solid bottom. But if you look at just the piece that we're slicing, Aaron says it looks like a washer, and that's correct. That's one of the common methods that gets used for finding volume when you have a space that's subtracted from the middle. We call it the washer method. And so you can see the shape that develops there. Anybody ever played the game Washers, like the backyard game? There's giant washers you toss. You do. Okay. Do you like that game?
I haven't played it in a long time.
Like, so I'm thinking I'm thinking.
Wait, it's the one with like the board and the holes.
Yeah.
Yeah.
So I'm thinking, like beanbag toss, you played that, right?
Yeah.
And then if you played the ladder golf one,
Oh yeah.
okay, and then the washers one. So I haven't done the washers one before. Is that fun?
It is fun. It's harder though.
It's harder than the others?
Yeah, because you have like a wash like that size.
Okay.
And you it's like you have to kind of throw it like a frisbee almost.
I saw another one this summer. People were playing like these blocks of wood standing up in the yard.
Oh, we played that too.
What is that?
So you have like all the blocks like in just like a random like group.
Yeah.
And you have to throw one, and like whatever you hit, you get those points. But if you miss them, you get like out or something. I don't know. It was really confusing. I only played it once.
If we end our units early, maybe we should have a day where we just play outdoor games.
Jordan has the game.
Yes.
Jordan has the
Jordan
game.
has it.
That wood
Okay.
game. The what?
Don't
You have that wood game.
Like
where
the
you
blocks
throw
of
the
woods
blocks
that
with
you
the
in
wood.
the yard and like throw them at each other.
We
But you have
played
like the
that.
whole bunch of them like stand
We
up,
played that on the 4th of
and then you gotta hit them
July.
with
I think-
another stick.
Oh, okay, yeah. I thought you were talking about a different one, but
Okay.
yeah, I have that one.
All right. Well, we'll
It's called
maybe make a list and see what we can do.
Oh, I know that game. I
Maybe we could schedule a date this summer and just get back together, have a calculus
yeah.
campfire and play some games.
I might be gone.
We should.
Yeah. All right. Cool. We'll do it. We'll schedule it. Yeah. Yep. All right. I'll put it on the calendar. All right. Let's look at the purple washer. Does it have thickness of dx or dy?
Yes.
It has thickness of dx. Very important that we identify right away whether it's a dx problem or a dy problem. And then we want to be able to, so we know that that's the thickness, but now we need the area of that washer shape. How would you calculate the area of that washer shape? Anybody know?
The area of the circle minus.
Yeah, the big radius squared times pi. That would be the area of the big part, right? But we got to subtract out little part. So it's minus pi r squared. Or in other words, pi times big R squared minus little r squared. So, and in this situation, what makes our large radius? F of x. So we have pi times the big function f of x, or the function on top squared, okay, minus g of x, that quantity squared, dx. So that's going to be the volume of just simply one washer. And the beauty about calculus, again, is we could go from one washer to an infinite number of washers by simply slapping an integral on it. And that's that. We're going to do two examples and let you kind of work on things from there. We'll flip it over, find the volume of the area bounded between y equals x squared and x equals y squared rotated around the x-axis. This is a very, very, very famous type of problem. It's used a lot. And I have two functions here, y equals x squared and x equals y squared. What is y equals x squared going to look like? Parabola like this. And what is x equals y squared going to look like? Okay, so I want to make a point here. Because Ray is correct, this would be the square root of x is equal to y. It's the same thing. But we notice x equals y squared is a horizontal parabola. So if we were to draw it like this, the fact is we don't really need all this portion of the graph, do we? I only need a small portion. So in this situation, I wish I could just erase part of it, but whatever. So notice that really all I'm concerned about are those two parts. Everybody agreed? Because that's the area that they intersect. So we're going to go ahead and shade in this region right here. And I'm going to rotate that around the x-axis. As I rotate it around, I have this region down here. Okay. If I were to take and try to draw what this looks like when it's rotated, again, I look at a small rectangle in the original space. If I rotate that around, I'm going to get this empty circle on the inside, and then I'll get this filled in circle on the outside.
I don't see it.
Try again.
What are those two little lines?
So remember when we had two curves and we drew a rectangle between those two curves?
Yeah.
It's the same idea.
Oh, okay.
The washer actually comes from rotating that rectangle around. try a smaller one here. Is that better? Okay, so here we go. I see that it's a washer. Is it thickness of dx or dy? Dx. So I have pi times big R squared minus little r squared dx. Notice that everything must be written in terms of x. What constitutes the bigger radius? Which function is all the way at the top?
Y squared.
Yeah, it's x equals y squared. So I think it was Ray already said that you can translate that to y equals the square root of x, agreed? So that's what we want to use for the top is the square root of x. So we have pi times the root of x squared minus, and then what makes the lower part of the radius? X squared. And we integrate from what to what? Where do the bounds start? 0, and it does go to 1. If you notice, the coordinate 1, 1 is on both of those graphs, is it not? So 1 is the intersection point right there. We work this out, and we get pi integral 0 to 1 x minus x to the 4th dx. And we take an antiderivative of x, and we get x squared over 2. The antiderivative of x to the 4th is x to the 5th over 5. And so we have pi times 1 over 2 minus 1 over 5. Or pi times 5 over 10 minus 2 over 10. And I get 3 pi over 10. What do you think? I'm going to show you a method that I like a little bit better for doing this in a picture. For example, number 2. Example number 2 is what we will want to stop with. But so just to review, we started out this unit by talking about area bounded between two curves. Just take the top minus the bottom. And then yesterday we looked at, well, what happens if you rotate that around and create some volume? Today we're saying, well, what if you subtract the middle? So you have area between two curves. You have this disk method. You have this washer method. Whoop. You have this washer method. And then we only have one more after this. Okay, so there's 4 methods total that we'll be looking at. So, all right, let's do the last one here. Find the volume of the area between y equals 1 over x and x equals 2 and y equals 2 rotated around the y-axis. What's different about this problem? Yeah, you're rotating around the y-axis. What does the graph of 1 over x look like? Remember, the reciprocal function looks like this. Okay? And we are concerned about this region right there. So I'll draw this. We have x equals 2, so 1, 2, and y equals 2, 1, 2. And so the region that we are going to be looking at is going to be right here. I used to really make students come up with that region on their own, but it just doesn't happen very much on the AP exam, so I'll be providing those regions for you. I still think it's helpful to not include them in the notes, that we would, think about how that's composed together. I'm going to rotate that over to the other side, so I'll draw that shape. It's a similar shape right on the other side. Boy, that gets me every time, doesn't it? And as we rotate it this way, we're going to kind of end up with this shape. I'll do my best to draw it. Let everybody get the sketch real quick. Okay, best practice for organizing your work. This is something that they enjoy seeing on the AP exam. All the work that we show is something that they want to see. And without a doubt, it's nice in this situation to actually draw a washer on the side. So I'm going to use this washer. And you don't have to draw, the three-dimensional aspect to it. I usually do just because I get caught up with the whole deal. It's kind of fun. But draw a little bit of width there. And I'll show you what's going to help us in our framework, okay? What I like to do then is I like to draw kind of edges to show where these markings come from. So, for example, what makes up this part of the washer? What makes up that line? X equals 0, or the y-axis, right? So this is x equals 0 right there. Now, notice that the area that generates that happens on the right side of the x-axis, correct? So I'm going to draw a marker here, and I'm going to draw a marker here, okay? Just so we understand, see where it comes from. And this is going to lead us in because the next lesson on Thursday changes things a little bit.
Okay, wait, so what is the middle line?
The middle line is the y-axis, which is the equation x equals 0. This one?
Yeah.
We're going to talk about that in just a second.
Okay.
Okay, is the thickness vertical thickness or horizontal thickness? Vertical, so therefore we have a dy problem, not a dx. All right, what makes up this part? X equals 2. Notice how both of these are equations of x equals. Both of them are x equals, so that means that this one is going to need to be an x equals. It's a dy problem, so it's going to have the y variable in it. Notice what makes up this part, this edge right there, is the y equals 1 over x, correct? But I don't want to write it as y equals 1 over x because that doesn't match with the dy. So we will just say y over 1 equals 1 over x, and we'll then solve so it's an x equals instead of a y equals. If I cross multiply, I get 1 is equal to xy, and I divide both sides by y, and I get 1 over y is equal to x. Everybody see that? So the large radius is the distance from here to here. What's the distance between those two? 2. And then the small radius is the distance from here to here. And that distance is just 1 over y. Everybody okay with how I came up with those boundaries? So as we set up pi times big R squared. What is big R squared going to be? 4. Minus, what is little r squared going to be? What? 1 over y squared, dy. That is the volume of that little washer slice. And now I need to integrate in order to do an infinite number of them. Talk to the person next to you. Take about a minute and 15 seconds. See if you can come up with the boundaries. Go, talk. What do you got for the boundaries?
How is it?
I was thinking this way first, and then I was like, oh wait, no, it's 0 to that way.
So it'd be 0 to x.
How is it 0? It's not touching the bottom.
I would be, I guess,
I need a big bigger.
yeah. Yeah, I think so.
Take about 30 more seconds. See if you come up with a guess.
Yeah, you have to do it correctly because it's in terms of water.
Five, four, three, two, one. Okay, so when you determine your bounds of integration, you never look at the side that you rotated against, okay? So one common thought might be, well, we're going to go from x equals -2 to x equals +2. But we know that they're y values. You always look at the area that generated the start of the shape. So we always look at this. This coordinate right here is 2, 2. Agreed? This coordinate here is an x value of 2. If the x value is 2, what's the y value? 1/2. And then this has a y value of 2. If the y value is 2, then the x value is 1/2. That's the 3 coordinates of that shape. When we integrate according to dy, you are looking at the y values of the boundary. So we would go from 1/2 up to 2. That makes sense? You always come back to the original area. Don't get confused with how you revolved it. Okay? That's our shape. That's what we're going to integrate. Fortunately, we're really good at integration. No big deal for us. We take the antiderivative. What is the antiderivative of 4? 4y. What is the antiderivative of 1 over y squared? We're just going to have positive 1 over y. Does everybody see where we get that? The 1, so it's a negative y to the -2 is what we have right there. If you take the antiderivative, you raise it by 1. And so you get negative y to the -1 divided by -1. Negatives cancel, you get 1 over y. Okay? So that's kind of handy right there. We like that. And so now we will plug in our values. We plug in both 2 and 1/2. As I plug in 1/2, I get 4 times 1/2 is dos, which is Spanish for 2. Plus 1 over 1/2 is 2. So 2 plus 2 minus, wait, I'm sorry. I just plugged in 1/2 right away, didn't I? We'll put that over on this side. Sorry. Sorry. We'll put that over there, okay? So we'll go back, we'll plug in 2, 8 times, or 4 times 2 is 8, and then 1 over 2 is 1/2. Okay, that's better. So we have pi times 8 plus 1/2. So I don't know, 8.5 minus 4 is equal to 4.5 times pi, probably more commonly known as 9 pi over 2, as 4.5 is 9 over 2. A little bit better? So that brings us to the conclusion here. I want you to look at your homework. You have enough to work on at this point, there's no question. And if you notice, yesterday we looked at volume by discs. You are ready to move over to volume by washers. Is volume by washers part 1? Because on Thursday we're going to look at a second part, okay? But time to kind of get your feet wet with it and move on that. And we'll go from there, okay?